This is actually related to your perspective projection itself. What happens in OpenGL is basically it will be having some perspective kind of transformations, with the help of which you need to remember some normalization techniques which are actually called as coordinates. Check out the point here. The final step in the perspective transformation process is to map parallel pipe to a normalized view volume. That is nothing but you are just mapping some parallel lines with respect to the V volume, whichever we studied in the previous class. Check out the diagram which is being represented. The initial object, this is an initial object and this is an view volume. Now you have to map this particular object towards this view volume. At this time we will be using normalization with the help of perspective projection. If suppose this is the clipping window, that is the window which is to be clipped, is represented in this object with respect to different view, that is x, y as well as z view, which consists of a reference point which is used for that kind of projection from the initial point, that is the between point, center point with respect to the clipping window. With respect to this clipping window, as I told, there will be two important points which you need to remember, or I can say if a clipping window is being drawn, there are two important points. One is x minimum, y minimum, z minimum, and other one is maximum parts. If I suppose take these are the 2 points with respect to the object, the projection reference point with respect to these point can be referred as the point which is to be clipped with respect to that particular object. So as I told, once you got these points, you can start clipping that particular area. Once the object is being clipped, you will perform normalization so that you can map that particular clipping window towards the normalized view volume. That is this view volume, that is nothing but whatever the clipped area is being done, it is actually shrinked so that it will be fit into the all the axes with respect to xyz plane, which consists of values -1, -1, -1, and 1, 1, 1. This basically tells you the point values with respect to x minimum and x maximum. So this is how normalized perspective projection with respect to transformation coordinates are being converted from one part to another part. Basically, it depends on which kind of axes you are using with respect to each other. So, with the help of this transformation coordinates, you will be able to convert the what I can say, the clipping window towards a normalization part, that is with respect to the view volume. In normalized perspective projections, if I want to consider this in the matrix form, this is represented as scaling, that is matrix of xy scale, that is with respect to the points with respect to the shared transformation towards its diagonal, where it is being replaced with the identity matrix. Then once as we studied different perspectives such as parallel, oblique, and all, so this coordinate is being represented with oblique perspective with respect to scaling in the matrix form. So finally, how will I get the normalized perspective with respect to that particular object? I am just taking the product of both the matrices mxy scale with respect to m oblique perspective. This basically depends on the sharing part with respect to the minimum as well as maximum part. So you can check out here, they are just taking xw minimum plus maximum and then dividing it by to taking the mean of it. Then you will get an complete matrix with respect to the normalized perspective. Then, as I told, the comparison between perspective versus parallel projection. If this question is asked, you can actually give the theory part with respect to perspective and parallel projection as well, and then you can represent those projections diagrammatically also. So we'll check out how what is the difference between this if I compare perspective to parallel projection. What happens in perspective projections is basically the size of the distance varies a lot, which basically looks if it is real. If you are taking and implementing perspective projection into a real-time scenario, the size between the distance of the object as well as the center point varies a lot. That is actually one of the cons, I can say, advantage of perspective projection. Some of the disadvantage with respect to perspective projection when it is being compared with respect to parallel projection is distance and angle are not preserved. So this is the point we studied, where we not much consider the distance as well as angle of perspective projection. Then in parallel projection, lines do not remain parallel. So we studied this as the lines are being preserved parallelly, but in general, if we consider, the lines are not actually parallel in perspective projection. What about in parallel projection? What is the advantage? Exact measurements can be done. Then parallel lines remain parallel. That is an advantage. Then in this, as here, distance as well as angles are actually not preserved. Similarly, here distance is calculated and preserved, but the angle of that particular area is not actually preserved. Then it is less realistic looking. That is, it is not much implemented in your real-time scenarios. Then that is the simple comparison between parallel projection. There are some of the points as well with respect to parallel as well as perspective projection. I have given it in the notes as well. You can go through it. As I told, distance is an considerable factor with respect to both the projections, that is perspective as well as parallel projection. Then proportion, you can give one difference as a proportion as well. Then you can give the types of projections. If you come towards perspective or with respect to perspective projection, the types are 1, 2, and 3 point perspective projections, which we studied. Then if you come to parallel, this orthographic as well as oblique projections are its types. Then what happens if you consider parallel projection for application parts? Parallel projections are basically suitable for architectural drawings, where actually measurements are very much important. That is one of the application. Whereas perspective projections, it is used to create realistic views. That is, you can create any kind of views with respect to perspective projection. If you can consider as a 3D image, if you want to draw, you can consider perspective projection and then implement it. So this is actually a 5-marker question. That is the difference between parallel as well as perspective projection. Then we'll move on to the next topic, that is the viewport transformation as well as three-dimensional screen coordinates. Once the transformation is being completed with respect to three-dimension viewing, we'll come to the screen coordinates. Once this is done, what I can say, whatever the normalization of coordinates is done, we'll move on to viewport transformations with respect to different types of projection. That is, once we complete this type of transformation, we actually we can start clipping their efficiently so that we can get some that normalized area. How that normalized area is being drawn, that is, contents of the normalized area is being drawn. As I told, once the transformation is being completed, clipping is performed efficiently with respect to that object, with respect to normalized view volume, which can be transferred to screen coordinates. Now you are done with whatever the inner working part of the object. Now you want to display the screen coordinates with respect to object. Like you are starting to draw that particular object onto the screen. So how you can do that is, you should first consider the normalized view with respect to that particular area, and then you can transfer that particular object to the screen coordinates. Basically, the contents of the normalized view volumes is actually transferred to the 2D screen, which has this formal transformation. That is, you are considering M as an object which consists of normalized view volume with respect to the 3D screen. That is, with respect to 3D screen coordinates, the matrix is being represented. The lower left corner of the viewport screen area position is given by x minimum as well as YV minimum, that is, which is being used here. If you are displaying the object onto the screen, the lower left, that is the left part, the down part of your left part is being given with respect to XV minimum and YV minimum with respect to 0, XYZ axes. And then upper right part is given with respect to XV max, that is, where is XV max? Yeah, this is XV max as well as YV max. These two values, that is, it is basically telling the screen minimum as well as maximum values. Then, as I told, it consists of some XY positions as well, right? Because it consists of minimum as well as maximum values. It consists of positions with respect to SY, XY, which basically gives some buffer where a particular memory is being stored with respect to which the color information of that particular point can be stored. And we use something called as depth value for each screen point, so that you can store that particular buffer area, which is actually called as depth buffer. This depth buffer is used to store that screen points with respect to buffer area. This depth buffer is actually seen in your module, in the last of your module 4. Whenever we move towards your next slides, we'll come on studying about this depth buffer. This is a separate topic where we see in detail about depth buffer. So what are the functionalities of a refresh as well as a depth buffer is, as I told, if each x, this is the maximum value, if this is the minimum value, x as well as y position on the viewport, whatever the screen you represent is called as an viewport there, it is basically representing a refresh buffer position, that is called as refresh buffer, which actually includes the color information for that particular point to be displayed onto the screen. And it consists of a depth value as well for each point, which is stored in that particular depth area, which is actually called as depth buffer. So these are the two terminologies you need to remember with respect to the viewport transformation as well as 3D screen coordinates. Then that was a simple conversion with respect to viewport transformation, where we have represented the matrix form of it. Then we'll come on to your software part, that is OpenGL 3D viewing function. So this is one of the most important questions with respect to this module. By comparing with other questions as well, they can ask you for 8 to 10 marks. I'm telling you this. Yeah, in your internals also, I might give this question. I'm openly telling, because this is one of the important question. I'll share you the question bank as well. So this is one of the important question. This might be asked for your internals also. Yeah, for 4 to 6 marker question. The question is stating, explain OpenGL 3D viewing function. I have already told you 1 4 marker question now, right? So do remember this. And whatever the questions are included in the question bank, the same questions might come to your internals, okay? So this is actually 8 to 10 marker question. As we had different OpenGL 2D functions with respect to module 2, similarly, we have three-dimensional view functions with respect to OpenGL. What is the first functionality represented in your syllabus is, it is the transformation function, that is lookat function. Once we study this lookat function, we'll check out how this frustum, this is actually explained, but again, it also comes under the three-dimensional viewing function as well with respect to the view volume. With respect to viewports also, we will study. Then we'll move on. What is GLU lookat function? Before moving to this GLU lookat function, you should remember what is matrix mode function. Because it is actually linked with GLU lookat function. Matrix mode function is basically used when we want to alter some model's view. That is, if this is a model which you want to represent, if the view of the model should be rotated or tilted, what kind of view we use here is, that is matrix mode view. That is, you put that particular view into a matrix format. After you put that particular thing in a matrix format, As we know, whatever the initial matrix consists of, it basically consists of an identity matrix, right? Then once the identity matrix is being initialized, then scaling as well as translations are being performed onto the particular object's viewer. The viewer might be your camera or your user or anything. So this is how the matrix mode function works, where it basically depends on the position of the camera as well as the position of the object as well. So, what is this lookat function? I can tell this is an method where you are representing different objects. This is actually called as a direct method, which actually specifies the position of the camera. It basically defines the viewing transformation. As you all know, the question only says it is a viewing transformation. It is defining the viewing transformation. It is a direct method. It basically specifies the position of the camera. It basically, this lookat function comes into consideration only when the viewer is there. In this case, the viewer is what? The viewer is the camera here. So the position of the camera matters a lot with respect to lookat function. As I told, the positioning of the camera is done with the help of this particular function. Then check out the definition function here, how it is being defined. It is being defined with respect to ix, iy, iz, with respect to which position, that is at x, at y, and at z, then up x, up y, and up z. So these are the parameters represented with respect to GL lookat function. How? Sorry, I have missed here. There is you missed here. GLU lookat function. It is GLU lookat. Okay. What are these parameters? Ix, Iy, as well as Iz, it basically specifies the eye position. That is, if the viewer is a human being, if this is the position of the eye, this basically represents this. That is the position of the eye with respect to x, y, as well as z. Then we have something called as center x, center y, as well as center z. That is with respect to this at x, at y, as well as at z. This basically gives the reference points position. It specifies the position of the reference point. That is, from here, the viewer is looking at the position, and this is the reference point of the object to be seen. So this reference point is being represented with respect to at x, at y, as well as at z. Then there is something called as up x, up y, as well as up z. What does it do? It basically specifies the direction of the vector, that is at some space point which is actually visible to the camera as well. At that position, this up x, up y, as well as up z is also represented. So the GLU lookat function provides an alternative to translate f as well as rotate f sequences for positioning of the camera. As the whole throughout function is used for positioning, you can actually beat, translate, as well as rotate function with respect to GLU lookat function. How to define the viewing transformation, as I explained in with respect to the diagram. Okay, so what happens in GLU lookat function is it basically creates a viewing matrix. Do concentrate on whatever I'm telling. This function actually creates a matrix that is actually an identity matrix from an eye point. That is, it will consider this eye point and then create a matrix where a reference point is being indicated with respect to the scene, which actually tells you the center of that particular scene or the object. That is the functionality of GLU lookat function. What it does, it basically creates a matrix with respect to the eye point, and then it will check out the reference point, that is the center of that particular object, and then create a matrix, that is and then it creates a vector, sorry, not matrix, and it will create a vector which is actually called as up vector. Then what happens once you got this particular matrix? Then mapping of reference point is done. Similarly, the direction is also calculated with respect to the up vector. So this is how GLU lookat function works. If you want to code this GLU lookat function, you should use first the matrix mode, because the matrix should be initiated. The parameter for matrix mode should be GL model view, because you are defining the model here. Then I will load the identity matrix and then define this function, that is GLU lookat function. So this is how GLU lookat function works. Then we have something called as frustum. As we have studied this before also. So what is what does this frustum does? Basically, it describes the perspective matrix that produces a perspective projection. This frustum produces a matrix which actually consists of perspective projection. That is, whatever the camera is being placed with respect to that particular object, perspective projection can be defined in this way, where it consists of minimum, maximum, as well as all the part of that particular area, that is side, right, bottom, top, left, and all. So that kind of projections are being defined with respect to GL frustum. So this is the function which consists of minimum value with respect to x coordinate, maximum value with respect to x coordinate, minimum value with respect to y, maximum value with respect to y, and it also gives the near and far area of that particular object. So this is the representation of perspective projection, and then this is an example of perspective projection. And whatever the object with respect to the different space is also recorded into the camera, at that part I can say the empty space is actually called as a frustum with respect to the viewing point. As I told, it depends on the positioning of your viewer. It depends on the position of the camera as well, so that you will get different perspective projections, that is different projection with different areas. Then how OpenGL supports viewports as well as display windows. So what is a viewport? The sub window into which the current graphics are being drawn, I can call it as a viewport. How viewport is being defined with respect to OpenGL is it consists of 4 parameters with it: x, y, width, and height. Width and height basically gives the viewport size, and xy basically specifies the position. What does this xy tells? It specifies the lower left corner of the viewport. If suppose it is a rectangle in pixel, then the initial value is 0. What does width as well as height specifies? It gives the size of the viewport. Check out the example of the how viewport is being given with respect to the displaying window. If suppose this is your system, what is the viewport here? The area which is being clipped is called as a viewport, with respect to which I can define it as a clipping window as well. And check out what is x and y values here. If the initial value will be 0, height and width of that particular viewport is actually called as h as well as w. So this is the graphics window in which you are displaying the clipping window part. So this is how OpenGL viewports as well as displaying windows works. Then we are almost done with the 70% of your module till here. If you complete with just this functionality, that is GL frustum, almost 70% of your module 4 is done. Where we saw the important concept of 3D weaving pipeline, we saw coordinate parameters, then we saw the transformation of world to weaving coordinates, then projection transformation, orthogonal perspective, in which we included parallel transformation, that is parallel projection as well. Then in today's class, we saw some part left with respect to perspective projection, and then viewport transformation and 3D screen coordinates. Then we saw some of the OpenGL 3D weaving functions as well. So now we'll move on to the next topic of your module 4, that is visible surface detection methods. That is, what are this visible surface detection method? Can someone tell by looking at the name, what is visible surface detection? No? Okay. If I want to tell, in this visible surface detection, we will be studying some of the algorithms with the help of which you can classify the surface of the area. Suppose I have given a set of 3D objects and some specifications with respect to that particular object. Now I wish to determine which lines are on the surface of that particular object are visible, which lines are not visible on that particular surface. So doing this process, whatever you process with respect to finding which is the visible line on the surface and the invisible line on the surface, this process is actually known as hidden line elimination or visible surface detection, where you are finding the visible lines as well onto the surface, and invisible lines also onto that surface. I can define, this is actually the definition of visible line detection, that is visible surface detection also I can call. So there are some of the algorithms which we can study, which are actually classified with respect to the algorithms, which is, there are two important algorithms. One is backface detection as well as depth buffer. As I told, we saw a small flashlight on depth buffer in the previous slide as well. So we'll be studying this method in detail. Then we'll be checking out some of the functionalities with respect to OpenGL. Then, so check out here, what are visible and hidden surfaces? Suppose this is a viewer. It consists of some viewing direction. Because the viewer is directly facing the object, I can see there is a straight viewing projection there, where the viewer is directly facing the object. Viewing direction can be huge. It consists of huge number of angles, where this might be seen in another way, this might be seen in another way also. But how to find out this particular, if there are visible and invisible lines in that particular object? First, the area which is being projected here can be eliminated because it is totally shaded here. Finally, the object which is being seen to that particular viewer is this kind of object is being seen. This basically, here basically application of algorithm is done. That is, you are applying different algorithms so that the viewer can see the visible as well as hidden surface of that particular area. So moving on to the introduction part of visible surface detection. So in computer graphics, how you will determine what is visible within a scene from a chosen viewing position. That is, how you will determine the visible part or the visible lines in that particular object in given position. So you will use some algorithms which is used to identify and display visible objects. Why these algorithms are basically called as visible surface detection methods or hidden surface elimination method. Then this algorithms, whatever the visible surface detection algorithms are basically divided into two. One is object space as well as image space method. What happens in object space method is it is basically implemented with the help of physical coordinate system, where directly the object is being focused. That is, object is being described. What happens in image spaces? It is actually coming onto the screen coordinate. In the object space, the physical coordinate system is being used, whereas in image space, I can take only the screen coordinates with respect to the system. Then check out, basically in object space, it compares objects and the parts of the object to each other with the scene definition, so that you will determine which surface consists of what kind of lines, that is visible or invisible lines. Then coming on to the image space, basically visibility is decided point by point at the pixel position. As I told, the screen coordinate comes into picture only in image space, but in object space, the complete object is being exposed. Okay, then check out the examples with respect to object space method as well as image space method. In object space method, what happens? It applies these methods directly on the physical coordinate. That is, directly, if this is an object, if there is a plant, it is considered as an object. The visible surface detection methods or the algorithms are directly applied on the physical coordinates of this particular area. Whereas for image space methods, you are using some viewports, that is from the viewer. There is some viewport with respect to which methods are being applied. That is, it is not directly applied to the object, it is applied to the viewport. That is the image which is being taken with respect to that particular object. So this is the comparison between object space as well as image space method. Then there is some difference also with respect to object space as well as image space. In object space, it basically compares the visibility, where it basically in image space, it basically compares the pixel visibility. That is, the object part compare visibility in the sense it is just comparing the object size or object coordinates, but where it comes into pixel, the screen coordinates comes into picture there. Then there is some system used here. In this object, we use line display algorithm. In image, we use line surface algorithm. This is one of the example we study, that is raster scan method here. Then how we use object space method, we use this in geometrical relationships among objects. We'll use this in image processing. This is one of the example. Then how the calculations is done here, this is in image space, pixel to pixel calculation is done. Here the floating point value with respect to the object is also done. There are some examples with respect to which these methods. Object space method is a backface detection method, whereas image space method is a depth buffer method. So these are the two examples. As I told, there are two algorithms we'll study. One is backface detection as well as depth buffer method. So these are derived from these methods, that is object space method, image space method. While you are writing the answer for backface detection method, if you are before explaining the algorithm, you need to specify this backface detection method comes under object space method, where only the physical coordinate systems are considered, whereas depth buffer method comes under image space method, where screen coordinate systems are considered. Do remember this point. You need to specify which are the methods which are being implemented with respect to those algorithms. So these are the two important algorithms with respect to the module. Then we'll study how these detection methods use some elimination kind of techniques. That is list of visible surface detection or hidden surface elimination method. There are huge number of algorithms which are used, but in your syllabus there are only two algorithms. One is backface detection as well as depth buffer method. These methods are also good while compared to this, but in your syllabus only these two are explained in detail. Check out here, this Z buffer method is also called as depth buffer method. Do remember, they might ask you as Z buffer or depth buffer as well. So these are the two algorithms we are studying in this module. One is